Yeah, so thanks for the introduction. I'm Justin. I work at Facebook New York, the engineering office here, and I work on places data, and really just trying to improve our places database. So this is sort of a snapshot of what our database looks like if you map it out to the world. So you can see you can map out every country in the world using check-ins from our places data. And penetration into not just sort of the bigger, more populous countries, but also areas outside of that. As an example, here's sort of the 6-month moving growth of our location product in South America. And you'll see that this is a week's worth of check-ins when we first launched the product. And every 6 months after that, it continues to grow. Until we're really representing like most of the major population centers in places that don't have a huge connectedness in terms of internet growth. So our places data is stored as a graph. So we sort of have our roots in social network where we have people and connections between them that form a structured graph of data. And what that's evolved into is really this n-partite graph now, which is people, but we also have photos and places. And they're interconnected in various ways, but there's also sort of this fabric that connects them together through status updates, where you can tag locations with statuses, and you can tag people and associate photos with locations as well. So that's what really creates this connectedness and allows us to have this really rich places or location structured data, which allows us to answer really interesting questions about explicit retrieval of, show me all the restaurants in New York. And we know not just that a restaurant is in New York, but we know sort of the hierarchy of places, and that New York City is contained inside of New York, and that has neighborhoods inside of it, but then also the ontology of topics associated with them. And then you can say, show me all the Cantonese places in this neighborhood, but then also like all the places that my friends have visited as well. So we have all of these connections, and we were able to surface really interesting structured queries as a result of it. So what that allows us to do is provide some interesting insight in terms of when we're doing some analysis. So this is an example of, you can get sort of county-wide maps of where people have affiliated Republican or Democrat, but we can go deeper than that, and we can look and see like what types of places are Republicans checking into or visiting, and what types of places are Democrats going to, and get these really interesting maps of, not just that maybe Dallas is Republican, but there's this sort of core of Democrats in the center that's surrounded by this Republican band of folks that are closer out in the suburbs. And then, really this is like a global database. So we have 1 billion active users, and a lot of these folks are using our location products. So we really have a true sort of global scale sample of what people are doing in the world. So you can see where are people traveling from major transportation hubs to other places, and get a real sense of sort of the beat of the world of where people are going from one place to another. So a lot of interesting insights you can get from our data. I want to briefly talk about some of the tools we're using, and then I'm going to jump into some of the like harder problems we're solving, some of the like deep machine learning problems we're solving. But quickly to go over the tools, there's really sort of 3 major classes: machine learning, which has a bunch of different subdisciplines within it that we're applying to these problem sets, and then crowdsourcing. So like I said, we have 1 billion people that are available to answer questions about places that they've interacted with, that their friends have interacted with, and then product solutions around how we surface this data, how we generate this data and collect it from our users to build like a really high quality places database. Like most real world data sets, our location data follows a power law. So really it's not exactly 80-20, but 20% of our places will get 80% of interactions or check-ins. And so this is why this hybrid model of crowdsourcing and machine learning really is very effective. With the machine learned system, it doesn't really care how many times someone's interacted with the place. It can make classifications, or it can fix data with a certain sort of fixed recall. It definitely having more information about a place helps with that classification, but you can sort of solve a broad swath of easy questions using machine learning. And then what we can do is take these crowdsourcers and focus them on the head of data, so that what we're doing is improving our graph proportional to the amount that people want to use it. So this has been a really effective method for improving this data set. And then quickly, talking about the technologies we're doing, we have our sort of a custom fork of Apache Giraffe that we're using to do a lot of graph learning. So we're doing clustering and some label propagation in Giraffe. And then we use a couple of different classification and regression packages, Vopal-Wabbit, SVMs, boosted decision trees, and really trying to fit the classification package to the problem we're trying to solve. Really, we need to be fast because we're trying to do it at scale and to apply it to many millions of examples. And then to scale, we're using MapReduce and Hive almost exclusively to apply these problems outside of maybe some of the graph learning that we're doing. In terms of tools for crowdsourcing, so we have sort of two modes of how we crowdsource. One is we ask all of our users very simple questions. We have a lot of surfaces along our product where we say, make a quick edit to this thing, give us, change the title, tell us that the topic is wrong. And so we have a lot of these sort of edit dialogues where you can edit any information on a place. And then we have sort of this core of power tool for power users of crowdsourcing, people who know exactly what they're doing and can make a lot of really well-educated guesses and judgments about places that allow us to have folks, take the inputs from the larger set of folks and make fixes to our database, especially sort of bigger places that people are interacting with very often. And then just a quick note about product changes that I want to continue to add this onto the pile of the tools we have available. Often a product solution is the better solution. If you can fix the incoming data stream, if you can ask for more information, that's better than trying to infer it later. You have someone at the point of creation, and then also ranking I sort of throw into the product bucket where you can, instead of a binary classification, you can also rank by that signal as well. As an example of, we've already deduplicated places, but choosing which of those places within the equivalence class is very important in terms of the way that the product looks. You might not want to choose the duplicate that's the closest to the user, but maybe it's a higher quality experience as a result. So anyway, so that's sort of some of the tools we're using. I just wanted to give a brief overview of that. Now I want to get really dig into some of the deeper problems we're doing. And I'll start off with deduplication. So this is a really difficult problem, and as a result of some of the early choices we made in our places database, we have a lot of duplicates that are in our system. It used to be that we build a really engaging product, which means if you can't find a place, you can just put a new one in by giving us a text string and a lat long, and that creates a place in our database, which isn't an ideal case, but allows you to be very expressive in status updates. But it results in, you can't necessarily find places that are misspelled. So both of these places are duplicates of San Diego Zoo. They're both far away. One of them is misspelled slightly. Some of them have information. Some of them don't have any information. And so figuring out, even to try to match these against the real San Diego Zoo is a hard problem. And then on the other end of the spectrum, this is all of the Starbucks in the United States. So there are chains that have just thousands of locations. Up at Grand Central, where our office is, we have 5 Starbucks within 1 block of the office, 5 real Starbucks. And one of them is underground, so you can't really even know where you are when you're checking into it. So it's very difficult to make an inference that that's a real place, and to solve a deduplication problem of 2 places with a similar name should be deduplicated, but Starbucks, it's very likely that those are different places. So that's some of the problems we're trying to solve. And then finally, there's this constraint where you're comparing every place to every other place, or you'd like to do this, right? So you want to do this pairwise classification problem of, is this place the same as this other? But when you blow up the space of all places compared with others, you get into this massive problem that even with one of the largest clusters of MapReduce machines in the world, you can't solve in any tractable amount of time. So if you look at just 2 of the major features of what you're trying to use for classification purposes, things that are close in physical distance are likely to be the same, and 2 things that are very similar in name are also likely to be similar. So you could say that if you were to maybe build a linear classifier, that you would have some classification bound that is in the lower left part of this space, right? But in order to determine this classification bound, you need to have a huge number of comparisons and build something that is essentially intractable. And to pile onto these problems, so you have a lot of different issues around what does it actually mean to be the same. So things could have very similar names and be very different, right? So New York Sports Club and New York Sailing Club, the edit distance is not too far off, but they're actually very different places. Things like Starbucks Grand Central. Is it a Starbucks? Is it Grand Central? What does it mean for something to be located inside of another place? And then, also just sampling. Like, how do you sample places? You can't just randomly pull a set of places. You need to think about all of the pairwise comparisons that those places could have. So sampling is a very difficult problem as well. The extremes are difficult. So like I mentioned, chains or lots of little clusters. How do you differentiate them from landmarks, which is one place with lots of duplicates, right? So you could have 20 places for the Statue of Liberty, and they're all duplicates of the Statue of Liberty. You could have 20 places for Starbucks, and that represents 10 real locations, right? So 10 small cluster versus one large one. And then you run this extra edge case of like what happens when you find the original McDonald's, which is essentially a landmark and a chain at the same time. So you have lots of duplicates of that place as well. And then you're making these pairwise calculations. You're saying, A and B are the same, B and C are the same, but you have this sort of equivalence class. You're essentially saying that A and C have to be the same as well now. You have to respect transitivity. So if they're not the same, you have to find some way to break that. But what happens when you add in a new node D that's connected to A and C as well, and you have this massive connected components group, and you need to figure out how to essentially develop clusters out of it. So in order to solve some of these problems, so going back to the beginning, so we're talking about how do we constrain the search space of places we want to compare against each other. Well, you can do a lot of things. There's explicit hashing, so you can essentially hash things down to say, these two places are in the same map tile. They're very close to each other, so therefore, their proximity in real space is approximately equal to the fact that they'll hash to a similar value. You can do randomized hashing. You can do sort of randomized dimensionality reduction to say, take large feature space of maybe textual features and reduce it into a much lower dimension space, and your hash functions then can have a likelihood of matching that's proportional to some of the similarity metrics you're using, similar to locality-sensitive hashing. And you can also just sort of start, with sort of a big brush and try to map down the space and then carve it down later as you go on. So starting big and then applying more and more computationally expensive methods as you further constrain your data set in smarter ways. You can use domain knowledge. These two places should exactly be the same or shouldn't be the same at all. And you can do things like import all of Starbucks data. They have an API. And so you can explicitly look at chains that really that are very difficult to handle. So what this does is constrains now this n squared space down to something that's approximately linear in the number of places you have. So you have, in blue here, these are all the things that have a similar hash function or have an equal hash function for textual features that is approximately similar to your name similarity metric. And then in yellow, you have tile-based hashing as well. So now what you've done is you can union these two together and essentially cover everything that the classification boundary will have, while keeping your domain small enough that it's tractable to do a real computation. In terms of sampling, you can limit your sampling to regional. You can pull down different regions and randomly sample different like cities or geographical regions, and then do pairwise comparison in there. You can classify first and then label the results of your classification. So you can sort of do after-the-fact assumption that, after-the-fact checking that your precision is in fact what you expected it to be. And then there's lots of great NLP problems you can throw at this when you're thinking about the New York Sports Club and New York Sailing Club. In New York, the word New York doesn't really matter as much. When you're near Grand Central, the word Grand Central doesn't matter that much. There's other types of words you can ignore. There's abbreviations you can say this is the same as that. And there's ways that you can do better in terms of when you get down to the point where you're actually doing comparison between names of places, that you can just be comparing the most important words from those two places. And then there's a lot of interesting geospatial features. You can look at the space-time distribution of check-ins for places and make sure that there's high distributional overlap between the two of them as a feature as well. And then, when it comes down to, so we've made these sort of pairwise classifications, right? We've narrowed down the search space that we need to do pairwise computations. We've run a classification problem. We found some great features. Now we have pairwise classifications, and we've set maybe some threshold to say that these things are likely to be pairs of each other. So now you have this transitivity problem, right? So you've got Starbucks and SF Airport Starbucks, and we're pretty sure that those are the same. But now we also think that SF Airport and SF Airport Starbucks is the same as well. And so, transitivity says then you're going to connect Starbucks with SFO, and everything's going to be put into one giant cluster. That's really not all that great. So, like I said, you can solve chains and landmarks specifically. You can constrain that problem out, and you can say don't deal with this stuff immediately or deal with it ahead of time. And then you can also add additional domain knowledge and constraints. You can say, these places definitely should or shouldn't be the same. But what you really want to do is treat this like a clustering problem, right? So you take the results of these connected transitive components, and you can cluster them and say, I want to have very high interconnectivity, but I want to decrease the amount of intra-connection, or I want to have high intra-connectivity and decrease the amount of interconnectivity weight between a lot of these clusters. And then hopefully you come out to something like this that says, these are 3 real clusters that are the result of the connections between all of these things, and then develop these and build them as equivalence classes or sort of cliques in your graph about of duplicates places. And so another problem we're solving is sort of the opposite problem of this, right? So disambiguation. So what this means is that you could have one Jamba Juice that's in the middle of New York, and maybe there's actually really 4 Jamba Juices. But instead of checking into the actual one that they should, maybe they haven't, a node hasn't been created or an entity hasn't been created for those new ones. And so you get to the point where you have people who are checking in, and these dots are all check-ins. You have 2 Starbucks locations, but only 1 entity in your graph, right? So you have 2 essential clusters of places that people are using as a proxy for the real location. So this turns out to be really just a clustering problem, although there are some difficulties in the end. So you'll run into problems where the Statue of Liberty, maybe you'll get a lot of check-ins in Battery Park, and you might get some on the shore, on the Jersey Shore as well. And you get to the point where things look like they need to be disambiguated, but they can't be. But outside of that, really it's just a clustering problem, and then there's sort of a product problem of the difficulty of saying, did you really mean to check in here, or explicitly moving user connections beyond that. And then the last thing I want to talk about just is some of the inferences we're doing, which is really sort of more of a pure classification problem. So one interesting thing that someone on my team did was figure out what places are good for dates. So we have, this is really like exemplary of like the breadth of data that we have at Facebook. So it's not just geospatial features. It's also, we have relationship status, what time of day people are checking into, the categories of places they're going to, their gender, and things like that allows you to, to say that, places that people check into at night with people that are of the opposite gender that maybe they're in relationship with or not, it's highly predictive of trying to figure out what places are good for dates and what aren't good for dates. So this allows us to build on explicitly just crowdsourcing data to say, fill in this checkbox of, is this good or not, and allows us to make inferences based on, connecting both the social network with our location network. And then, essentially, we're using a mixture of methods for this. Classification is the main one, but we also use a lot of graph learning. So we'll use sort of Giraffe to do a lot of label propagation to say that maybe places that have a certain type of feature, we can build a similarity metric between places and propagate those and say that others are very similar, in the same neighborhood, and then use those resulting features then to do classification. And then the last thing I wanted to touch on was just that evaluation is difficult, and I know a lot of people have questions about this. We use a hybrid method of evaluation. We have a lot of supervised classification. We need a lot of labeled data sets. We have a lot of qualitative metrics that we drive our progress by to say, like, how many duplicates are in the database at any given day. And then there's a lot of post-run labeling as well, just to make sure that what we've done is what we expected to do. So we use sort of a tiered method of, I think a lot of people use the first and the third and sort of hand labeling, and then they'll send it off to Turk. What we found is there's like this middle ground of actually hiring folks, and it tends to be more cost effective in the long run in terms of spinning up the training and teaching of people to label good data sets and provide that data for us to train our classifiers. Anyway, so that's my presentation. I guess we can do, if people have questions, they can grab me out in the hall later. And yeah, that's it.